Hello, and welcome to my series on building system architectures in C. So today we are going to be talking about multi-threading, and specifically we are going to be building what is called a thread pool. In traditional multi-threading, what you are doing is essentially allowing your CPU to operate on more than one task at the same time. And this is great for improving performance or doing some simultaneous calculations, but it has a certain liability to it that we're going to try and solve with a thread pool. So if you imagine having an unknown number of tasks to do, and your program will essentially create a new thread for every single one of those tasks, then you have the potential to have many tasks come in all at once, and this is going to slow your system down exponentially, because sometimes having many threads doing something is not faster and is more resource intensive than just doing them one thing at a time. So what a thread pool is going to do is define a finite number of threads available, and then it's just going to pull from that pool to do any work that we assign it. So that's what we're going to be building today, is this finite pool of threads that we can pull from. So what I'm going to do is create a new file in my system folder of this library, and I'm going to call it thread pool. And we'll start off with the .h file, and I'm going to need to include the pthread.h header file. And we're going to define a struct called thread pool. And our struct is going to need to have a few properties. And some of these will probably be foreign to you, but as we go, their utility will become more obvious. So I'm just going to put in the properties that it needs, and I might give a brief explanation, but you will see them in practice in just a moment. First thing we're going to want is a definition of how many threads there are going to be. So we'll have an integer called num_threads. And we're also going to want to store the state of this pool. That's going to make a lot more sense later when we actually have these threads doing something, but we want to have a active or inactive state of the pool so that the threads know if they should continue running. So I'm just going to use an integer 1 or 0 here. I could use a short int, but I'm just going to use int. It's just going to be a 1 or a 0, but I'm just going to use an int. So we're going to call this active. And then we are going to need a queue. So I've defined my queue in the data structures library or section of the library. So I'm just going to include that in here. So we are going to include data structures /lists/queue. And the reason we want a queue is that the way it works is we are going to have this list of tasks for the pool to complete. And as we get new work for the pool, we are just going to put it into the queue. And then each thread is going to check the queue and try and take out some job. That way it will know what to do next. And I'm going to use a queue for this because it is a first in, first out data structure. So whoever asks for a job to be done first will get that job done first. It's a pretty reasonable thing to do. You might want to implement a different data structure here, but I can't really think of any case where I'm going to want to put in a job first and then let others take precedence over it. So I'm going to use a queue. So we'll have struct queue work. And now we're going to need a list of threads. And since we don't know how many threads we are going to have, we're going to need to define an array of an unknown size. And to do that, we're going to use a pointer. And this is going to be of a data type that comes in the pthread library. So this is going to be of type pthread t, and we're going to call this pool, but it needs to be a pointer. And the reason for that is we can define an array of unknown size by using this pointer. We can use malloc, or memory allocation on the heap, to actually make this array whatever size it needs to be, and then this pointer will just point to the beginning of that array. So next we're going to need two additional data types that are a bit strange and you're really going to want to see in practice. I'm just going to define them and I'll tell you basically what they do, but it's going to seem kind of strange. The first is called pthread mutex. And the mutex is a thing that's going to make something thread safe. So if we think of our queue, for instance, let's say we have two objects in the queue, and we have two threads running, and both at the exact same time try to pull the first item out of the queue. You're going to get some weird results there. Either they're both going to take it, and you're going to have two things doing the same thing, or one will take it slightly sooner, and the other will pull a null out. It's not a good idea to just have random threads operating on this data structure. So what I want to do is use this mutex to essentially lock the data structure so that it only allows one thread to work on it at a time. This is called making it thread safe, and we are going to use that with a mutex. And I'm going to call this the lock. And then we're going to need one other data type, the pthread condition. And this is so that we can reduce the overall impact of a thread on our system. So essentially, what you can imagine the thread doing is entering an infinite loop. And it's just going to continue checking the queue to see if there's more work. And this is going to take a lot of processing power if it's just continuing to check the queue, especially if you have 256 threads all simultaneously trying to check the queue. That's going to be a lot of processing power. So what we're going to use is this thing called the signal. And this allows your thread to just remain idle for a period of time until it is signaled that it can continue. So that's the next data structure, and again, or next part of the data structure. And again, it's going to make a lot more sense when you actually see it in practice. Now, what is the thread going to pull out of the queue? It could pull out a specific parameter that we know ahead of time, or I can define another data structure to represent jobs in the queue. And all of these jobs will have a function and an argument. That way I can put different types of jobs into the same queue. So if I want my thread pool to do 5 different types of tasks, I could just insert this one structure in, tell it to execute the function stored in that structure, and the thread pool becomes much more dynamic. So I'm going to create a thread job struct. So the job structure is going to have 2 arguments. One is a function to run, and the other is the argument passed into that function. And I'm going to use void pointers here. The reason being, I don't really know what sort of function the user is going to want their thread to use. And it might have some return type that is an int, whereas another one has a character array or a Boolean value, whatever they are trying to have it return or whatever they're trying to pass into it. I don't know what those things are. So what I'm going to want to do is make this for the general use case. And so it will return a void pointer that can be null, and it will take a void pointer that can be null. That's what will make this usable in almost any circumstance. So it's going to have a function pointer, void pointer is the return type, and this is a pointer called thread job. And let's actually just call it job. And this is going to take as an argument a void pointer arg. And then we're also going to need to store the argument itself in the data structure. That way we can call it later and say put this argument in as the arg. So we'll have a void pointer arg. And that's it for the thread job. We are now going to work on creating these constructors. So let's first have a struct thread pool, and we'll call it thread pool constructor. And this is going to take a few parameters, or maybe just one. Yeah, just the number of threads, because the rest of it we are just going to generate algorithmically. And then we're also going to need something for the job. So struct thread job, and we'll call this thread job constructor. And this is going to take both parameters. So it's going to take a void pointer to a function called job, and void arg will be its argument. And finally, we'll pass in a void pointer to the argument itself. Now let's actually go in and construct our thread pool and the thread job. So we're going to start with the thread pool. So struct thread pool constructor num threads. Okay, what we're going to do first is define an instance of a thread pool. So struct thread pool, well, let's call it thread pool. And we'll return thread pool at the end. So what we want to do first is set the number of threads. So thread pool dot num threads equals num threads, and then thread pool dot active equals 1. I'm just going to assume that the pool is active when you create it. I might want to make it in the future so that no, actually, I don't think I will. You will always assume that it's going to start as active, and that's going to make sense why I'm making that decision in a moment. Now we have to actually create the pool of threads. So we're going to use malloc here. So thread pool dot pool equals a pointer to a pthread object that is established with malloc. And for that, I need the standard library. And we're going to pass it the size of a pthread array of the size num threads. So that's going to allocate space on the heap for our pool, and then we can actually initialize all of the threads themselves. So what we will say is for int I equals 0, I is less than num threads, I plus plus, and then we're just going to create the threads. So we're going to call the function pthread create. Here we pass in first a reference to the memory location where the thread is. So what I want is the address of thread pool dot pool and position I. So we're passing in that position I. Next, we can just pass in null. And to be perfectly honest, I don't know what this parameter or this parameter actually does. I know that in my circumstance, I don't need anything there, but I don't know what they are. So if you do know more about that, please let me know in the comments. Okay, so this is going to create our thread, but what we need to do is to pass in a thread function, something that the thread is always going to run. And we know that the thread is going to pull out of the queue and then execute whatever thread job is in the queue. But I'm not ready to define that yet, so let's just say it's going to return a void pointer, and we're going to call it thread job, and it's going to take a void pointer as its argument. We'll just use a prototype for now. Now, with a thread, the function that you pass to the thread is what the thread is going to execute. And it is going to always take a void pointer argument and return a void pointer. This makes sense because, again, you don't know what the user is going to want to get from the thread, and you don't know what they're going to want to give to the thread. So void pointers are a nice way to do that. But we're just going to pass in thread job as the actual function. Okay. Now let me go back to the header file. We now are going to need to create our queue, and we can just use the constructor I've made for that. So thread pool dot work equals queue constructor. And now we're going to need the mutex and condition. And these are a bit interesting to set up. So we're going to say thread pool dot lock equals pthread mutex initializer. And we're going to cast this as a pthread mutex t. Okay, I find that a bit strange. There's another function that you can call called the pthread mutex initializer, and you pass it the address of, in this case, lock, the mutex variable that you want to use. I'm not really sure what this does. I just know that that's how you do it. And this is going to initialize our lock. So it's a bit of a black box going on here, but that's okay. We don't strictly need to know that right now. Would like to find out in the future, but for now we're good to go. So thread pool dot signal is going to be equal to something similar. So we're going to cast the result as pthread cond condition t, and a similar call is going to be pthread condition initializer. That's going to initialize those two parameters for us. And I believe that is all that we're going to need. It is. So we have established all of these variables, and we have created all of the necessary threads. So now let's take a look at this thread job function. What is the thread itself going to do? So let's define it down here. Returns a void pointer called thread job, and we pass it a void pointer to an argument. And this is going to take something out of the queue, and then it is going to execute the job that is in the queue. So first we need to put it into a loop. Or is this going to take a parameter? When I execute this job, it's just going to pull it out of the queue. I don't think we need any parameters. We don't really need the arg here. So what we're going to do is first put it into an infinite loop. So what it's going to do is just continually wait for something to end up in the queue, in the work queue. And as soon as something is in the work queue, it's going to pull it out and execute it, and then it's going to wait for something else to end up in the queue. And it's always just going to continue waiting until we tell the server that it is, or the pool, that it is no longer active. So yes, we do need a parameter. So this is going to need a reference to the thread pool itself. That way it knows what pool it's working in, and it can check if it is actually active. So we're going to want to cast the pool as a thread pool before we do it, or that is to cast an arg as a thread pool. That way we can actually reference the object. So we're going to say struct thread pool equals casting this, our struct thread pool pointer, arg. And let's make this a pointer. So now we have cast the argument itself as a thread pool, or as a thread pool data structure. Now we can reference that thread pool. So we're going to say while thread pool arrow, because it's a pointer, active equals 1. That way we can end this infinite loop at some point. If we no longer need our thread pool, we can just turn its active to 0, and all of these will stop executing and they will exit the actual function, which will allow us to kill all of our threads. We're going to deal with actually killing them later. Kill them. So what we want to do is first pull a job out of the queue, but it needs to be thread safe. So we are going to call the lock first. So we want to actually lock the queue, pull something out, and then unlock it for the next person. So we are going to say pthread mutex lock. And we need to pass it a reference to the thing that we want to lock. So thread pool arrow lock, and we need the address of that. So that's going to lock our thread, so that this is the only thread that is able to pull from the queue at this time, and that's going to prevent the threads from stepping on each other's toes. So we want a struct thread job, and we'll call it job, and we're going to set it equal to, well, first we need a reference. No, we don't want a reference. We're going to set it equal to the casting of struct thread job, and then we want to pull the thing from the queue. So we're going to say thread pool work, and we are going to dot peek If you're not familiar with the functions that I'm using here, you should check out the data structures video I made on the queue. That way it makes sense what these are actually doing. But we're going to peek to get the first thing in the list, and we're going to pass it the address of the work queue. So thread pool work. So this is going to collect the thing we want. We need to dereference it to actually get the value. And what does it not like here? And it needs to be a pointer. So the work.peek is going to return a void pointer to us. So we need to cast it as a thread job pointer. And then I'm going to dereference it and set this local variable equal to it. The reason being, I'm going to remove it from the queue right after I have peeked at it in the queue. And if I remove it before I actually execute the function, then I lose access to the function. And if I try to execute the function before I remove it, well, then no one else can work in the queue. No one can get the next job until this job is done. And at that point, you might as well not be using multi-threading at all. So I'm going to copy the things stored in the queue into a local variable. And this is going to allow it to access or allow it to exist after I call this function, thread pool work.pop, and the address of the thread pool work. So my pop function is going to actually remove that item from the queue. I have to do these in 2 separate steps for reasons that I discussed in the data structures series, but I have now destroyed that node in the queue. So having copied it here, I can still access those functions. And now that we are done working on the queue, we can unlock it for the next person. So pthread mutex, and we want not lock, but unlock. And again, we're going to pass it the address of the lock. So now the next person can actually go into the queue and get some work. So this isn't perfectly asynchronous, or synchronous, I should say, because one thread has to wait for someone to get something out of the queue before they can get something out of the queue. But then once they both have gotten their thing out of the queue, they can execute those jobs simultaneously. So there are some caveats to the idea of this being synchronous, but largely it is synchronous. It is the executing of those functions in the work queue that is going to be synchronous, but they are going to have to take jobs out of the queue one at a time to prevent them stepping on each other's toes. Now that we have pulled that job out of the work pool or the work queue, what I want to do is check to make sure that there actually is a job function for them to execute. And the reason is that later, when I'm ready to destroy this, I'm going to want them to just all move through it. And they're all going to be pulling null values out of the queue because nothing else is being added. It'll make more sense when I get to the destructor, but for now, let's just say that I need to check to make sure that that job function actually exists. So if job.job, is that it? Yeah, job.job, that's kind of awkward. If that function exists, then we're going to execute it, job.job, and we're going to pass it job.arg. And that's going to actually execute the function that we have established as the job to be done. And then it is just going to come back into the while loop, so long as the thing is still active. Once the while loop ends, we are going to return null, because there's nothing we need from that. And the last thing I want to add is my signal. So we can think of a few steps here. So the thread is going to enter this loop. It is going to wait for the pool to become unlocked or the queue to become unlocked. It is going to check if there is something in the queue to be taken. It is then going to try to execute that thing, and it's going to come back here and wait for the thread to unlock again. And This is going to take a lot of processing time. So it's constantly just checking if things are in the queue. And if nothing is coming in, it's still there just burning CPU cycles. So what I want to do is after I have my mutex, I want to actually give it the signal. So pthread condition wait. And here we need to pass in the address of the condition. So address of thread pool. And we want the signal. And then we want to pass in the mutex. And that's because it's closely related to this mutex. So we need to pass that into the wait function as well. So the address of thread pool lock. So now we've added an extra step here. When work is added to this work queue, it will first send a signal to this signal variable to say there's something to be done. Then the thread will no longer be idle and it will execute the thing. And if you look at how this is working, if you imagine that we have 100 threads and all of the threads are waiting on this lock function, it unlocks and that allows one thread to come through. The other 99 are still going to be paused here. So we have one thread on this wait, but nothing has been added to the queue. Rather than allowing that thread to go all the way through, come back up here and let the next one come and go all the way through, we're going to have that one thread wait here until it gets a signal. Once it gets the signal, hey, something new has been added to the queue, then it will go through the rest of this. And that's going to save on a lot of processing time. So we have this infinite loop so long as the thread pool is active, where first we are going to lock the queue, then we are going to wait for the signal that something has been added to the queue, then it is going to pull something out of the queue, and then it is going to unlock it for the next thread to continue. And then if there is a job to be done, it is going to execute that job. Okay, so that is the thread job function that all of these threads are continuously going to run. And this allows us to put a variety of different tasks into the queue. So I can put one in that's going to print something to the screen, and then I can put another one in that is going to hit some API and get some information. And I can do all of these simultaneously in the same thread pool just by inserting new jobs into the queue. Since we have these jobs, let's go ahead and create a job constructor. So we'll have this return a struct thread job, and we'll call it thread job constructor. And I believe I already have the arguments here, so let's just copy and paste. And this is going to be a simple constructor where we're going to create a new instance. So struct thread job, and then we'll say job.job, that's a bit awkward still, equals job. That's really bad. Okay. Job.job equals job. I don't like that. So what's going on here? Job dot, why isn't it letting me? So I should be getting an autocomplete thing there. I think it's just making a mistake. Job.job equals, I should not call this job. Let's call this thread job. The reason it's saying job.job equals job is setting the function in job to be equal to thread job. And the reason all of this is not working is because job is a variable up here. So let's call it, what do we want to change here? We can call it thread job. You know what? I'm going to call the whole structure job, and we'll call this job function. And I'll change the name here. Yeah, sometimes the shortest names aren't the best. Especially in C, actually. I found that because of the way it works, a lot of these back-end functions that I define only in the .c file, that gives me that private inheritance, pseudo-private inheritance idea. It actually will conflict with functions of the same name in other .c files. So even though it is limited to that one C file, when you actually compile them all together, it becomes a little bit more messy. So I find that giving things long descriptive names is helpful in that. But we're going to call it job function. Then we can say job.job equals job function. I might go in and change these names later, but it's superfluous, so we're not going to do that here. And we'll say job.arg equals arg. And then we'll simply return job. Now let's talk about the destructor for these things. So the thread job doesn't actually allocate anything on the heap. So we can just let it go out of scope on its own, and we don't really need to worry about it. But the thread pool has some interesting problems with it. First of all, it has the queue, and the queue allocates a lot of things on the heap. And I want to make sure that there are no memory leaks, so I want to call my queue Destructor when I'm ready for this thread pool to die. And also the pool itself, we have some interesting things that we need to take care of. We need to make sure all of our threads end before we try and empty the pool. Also, the pool itself is allocated on the heap, so we want to free that. So we actually want a custom destructor for the thread pool. So we are going to call this a void function called thread pool destructor. And we're going to take a reference to the thread pool itself. So what we want to do first is set its active status to 0. That way, once the threads finish their task in here, they can exit and the function can stop running. So we are going to first say thread pool active equals 0. And that will take effect in all of these threads. So now we need all of the threads one at a time to finish executing this. So one will be waiting here and the rest of them will be waiting here. So we want to send it signals and also unlock the mutex. So let's just send it as many signals as there are thread jobs, or not thread jobs, but threads. So for every single thread, we're going to send it a signal that, hey, you can continue and you can finish executing. It's not going to get a thread job because hopefully the pool is empty, and it is going to find that the status of active has been set to 0. It's going to exit and hit our return null statement. So we are going to want to send that many signals to the thread wait, or the signal. It's kind of confusing with the words. So for int I equals 0, I is less than thread pool num threads I++. So we're going to send the signal that many times. So pthread condition signal, and we'll pass it the address of thread pool signal. So that sends 100 signals, which will allow all of the threads to finish executing this. And then we need to join all of those threads. That is going to actually bring them back into the main program. So if you think about it, on the program start, we have this one thread that's executing, and then we branch that off into a bunch of threads. And once they have finished executing their tasks, we want to bring them all back together into one, and that's a nice clean way of doing things. So we will also say for int I equals 0, I is less than thread pool num threads I++, pthread join, and then we want the actual thread. So we are going to address of, I don't think we need the address of, so thread pool I, and then null. We don't need to pass it anything there. So as you can see, this for loop has exactly the same parameters as this for loop. So why would I execute them this way? Why wouldn't I put both of them together? The reason is that if I put my join statement right after the signal statement, I might not be trying to join the correct thread. So if you think about it, if we have 100 threads, and let's say thread 22 is waiting. Where is this? Thread 22 is waiting here. I send it the signal. So thread 22 comes down, it finishes, it comes up, it says it's not active anymore, so it finishes its task. And then I try to free that thread. I'm actually going to try and free thread number 1, the first one in the array. And that thread's not ready to join yet, and it won't be. So what I want to do is first have all of my threads exit. I want them all to finish their function. Then I want to join them all in. And since I want to do those two things separately and completely one at a time, I wanted to use 2 separate for loops here. So they look exactly the same. It's going to double the number of iterations I need to do, but it's the only way to guarantee that all of the threads finish properly. Now that they are finished properly, we can free the thread pool's memory. So we'll say free, and we'll pass it we don't need the address of, we can just say thread pool. And then we are going to call the destructor on the queue. So thread pool work, and that actually needs to be passed into our queue destructor, passing it thread pool work, and we want the address of that. So that is our basic thread pool. It's not very basic. It involves a lot of interesting things with these mutexes. I think mutices is a better plural. And these conditions called the signals and the locks. We need to think about how these are going to be executing, and we need to take care when we are ready to stop. But this basic layout will allow you to create any thread pool that you need for any kind of task or a multitude of tasks. You can have this thread pool do hundreds of different sorts of things just by adding different functions into that queue using this thread job interface. Now, I'm thinking that it might be a good idea to create a member function of the thread pool called insert job, and it takes a job as an argument. And the reason is I could use the queues interface to do that, so I could call the thread jobs queue.insert, or I could say thread job.insert this. So actually, now that I think about it, I think that's going to be a better idea. That way, it gives you the feeling that you're doing that operation on the pool itself rather than on something that exists inside of the pool. So let's go ahead and do that. So it's going to return void, and it's going to be a pointer to a function called add work. And it's going to take a thread job as its argument. So what does it not like there? Okay. It wants this first. That do it? There we go. Okay. So let's go ahead and define this function in the constructor. So first, we want something to actually insert in there. So let's create a prototype. We will just simply make that so it is not a pointer anymore. And we can say in the thread pool constructor dot add work equals add work. And I'll probably change the name of that function in the back end, but it doesn't really matter. So let's define the add work function. So let's paste it in again. And in fact, we actually need another parameter. So struct thread pool pointer So we need a reference to the thread pool itself. And if you've been following along, you'll understand why I need to do that. But if this is the first of my videos you've watched, then the reason is that this is basically the self parameter that you would use in Python. You need a reference to the object that you're operating on. That way you know which object you're operating on. And since we're doing this in C, there is no default way to do that. You just have to do it manually. And in C++, simply by referencing a particular object, it knows that self is in there. In Python, when you define a class, you have to pass self in to all of the class definitions, but not outside of it. So in C++, you don't use self at all. In Python, you have to use it within the class. But in C, we have to use it both within the class and outside of the class. And that's just because it's a little bit more manual in that sense. So let's go ahead and add our parameters to the others. So we'll add that here. And we're going to add it here. And I apologize, I have once again forgotten to make the text bigger. So here is the bigger text, and I'm going to slowly scroll through this so that you have a chance to actually read it. When I program on my own, I like a small font, and then I always forget to do it when I come to the video, so my apologies for that, but we are remembering it now. I'm going to scroll through once more, and you can pause if you need more time to read these. Anyway, so let's go ahead and define the function. So we're going to take the thread pool, and we're going to take its work, and we're going to insert .push is what we want. And push is going to take a reference to the queue, a void pointer, and the size of the data that we want. So we're going to push in address of thread pool work. We're going to pass in a void pointer to the data. So the address of job and the size of job. And is my queue going to allocate space for that on its own? I think it will. I'm pretty sure it will. That's how I designed it. I just need to remember. So let's check the queue. List.insert. And I'm going to create a node. The node constructor. Yeah, you see, I chain a lot of these things together, and it becomes a bit confusing. Okay, so here we get the pointer to the data and the unsigned long. And yeah, so we do allocate the size of this. And so the data, even though here our job is a local variable that is going to go out of scope as soon as this function is over, the push function is going to call the insert function of the linked list, which calls the constructor of the node, which is going to allocate space on the heap for that data. So even though it's a local variable here, it becomes a heap variable later. So that's what I was double checking there. So this is really just renaming that function, and it's only for the purpose of making the actual interface of the thread pool a little easier. All you have to do now is say threadpool.addWork and put in the function that you want to add to it, or the thread job that you want to add to it. And the other way of doing it would be saying threadpool.work.push, and instead I wanted to just say threadpool.addWork. And it just renames that same function, makes it a little bit cleaner to work with. But that is basically all it is doing. And I think that is going to do it for our thread pool. And my next task is going to be going back into my HTTP web server and making that a multi-threaded web server. So I hope you enjoyed this video. If you did, please leave a like and subscribe to the channel, and I will see you next time. Toodaloo.